Hey space enthusiasts, ever wondered if there's more out there than meets the eye, especially when it comes to those rocky visitors from beyond our solar system? Today, we're diving deep into one of the most intriguing space mysteries, the 25 unexplained signals detected from interstellar asteroids. These aren't just random space rocks. Some of them have been emitting strange energy signatures that scientists are scratching their heads about. We'll explore what these signals are, why they're so unusual, and what wild possibilities they might point to. Get ready to have your mind expanded. Before we dive headfirst into the mysteries of those strange signals, let's rewind a bit and talk about how we even became aware of these interstellar visitors in the first place. For a long time, our understanding of asteroids was limited to those within our own solar system, rocky remnants orbiting our sun. Then came 2017, a year that truly revolutionized our perspective. That's when astronomers detected something entirely unprecedented. Oumuamua, the very first confirmed object from another star system to journey through our cosmic neighborhood. Its name, pronounced Oumuamua, fittingly means scout in Hawaiian, and a scout it was, revealing a new class of celestial travelers we hadn't fully appreciated. What made Oumuamua so extraordinary wasn't just its origin, but its incredibly unusual behavior and characteristics. Imagine something long and thin, tumbling end over end as it zipped past us at incredible speed. Its trajectory was unlike anything we'd seen from a typical solar system object, clearly indicating it wasn't bound by our sun's gravity. This bizarre shape and unexpected path left scientists scratching their heads and opened up a whole new field of observation. Suddenly, the hunt was on for other interstellar interlopers. While Oumuamua remains the most famous since its passage, we've detected other potential interstellar objects, often identified through the vigilant eyes of advanced telescopes like the Pan-STARRS survey in Hawaii and sophisticated data analysis pipelines that can flag these cosmic outliers. These powerful instruments and computational tools have become essential gatekeepers, helping us spot these fleeting visitors from the vastness between the stars. So, what makes one of these space rocks interstellar anyway? It really comes down to their journey through cosmic space. Asteroids that belong to our solar system follow elliptical paths around the sun like planets held within its gravitational embrace. But an interstellar asteroid is different. It's on a hyperbolic orbit, meaning its path is so energetic and so far from our sun's gravitational influence that it's just passing through, not bound to orbit our star. Think of it like a tourist just dropping by for a brief visit before continuing its long trek across the galaxy. This hyperbolic trajectory is the telltale sign. It shouts, "I'm from somewhere else." When we observe these objects, their extreme speed and the shape of their path confirm they didn't form here. As for what these travelers are made of, that's where things get even more interesting and, frankly, a bit mysterious. Without being able to land on them or even get close enough for detailed analysis, we rely on remote observations looking at the light they reflect or the wavelengths of energy they emit. Based on these observations, scientists believe interstellar asteroids could be composed of materials similar to those found in our own solar system's asteroids, perhaps rock and ice. However, the conditions in other star systems can be vastly different from our own. So it's also possible they hold exotic compositions, materials we haven't encountered before in our own cosmic neighborhood. Studying their composition, even from afar, is incredibly valuable. It's like getting a tiny sample from another planetary system, offering clues about the building blocks of planets around other stars and the diverse processes that sculpt these distant worlds. Each one is like a miniature time capsule, carrying information from its birthplace light years away. Now, when Oumuamua first appeared, and later other potential interstellar candidates popped onto our radar, scientists weren't exactly pointing massive radio telescopes at them hunting for alien broadcasts. That wasn't even on the table. The initial focus was purely on the fundamentals, figuring out where these things came from, how fast they were moving, and what they looked like based on the limited light reflecting off them. Think about it, we were just trying to confirm they were truly from outside our solar system and understand their basic composition and shape. The surprise wasn't just that we found one, it was the sheer oddity of Oumuamua itself. Its elongated shape, estimated to be perhaps 10 times longer than it was wide, was unlike any asteroid or comet we'd seen before, and its path, the way it accelerated slightly as it left our solar system, raised even more questions. Comets can accelerate due to outgassing as ice melts, creating a tiny thrust, but Oumuamua didn't show the usual signs of cometary activity. This unexpected acceleration without a visible coma or tail was a real head-scratcher. It forced the scientific community to pause and consider possibilities beyond the standard planetary science playbook. Could it be made of something highly unusual? Was there something else influencing its trajectory? This is where the initial intrigue began to deepen. These early, perplexing observations laid the groundwork for thinking outside the box, opening the door, even if just a crack at first, to contemplating explanations that went beyond simple, everyday rocks from space. Now let's get to the heart of the mystery, those 25 unexplained signals. It all began with the very first hint of something truly strange, a detection that sent ripples through the scientific community. This initial peculiar signal was associated not with Oumuamua, but with a different object, one of the later interstellar candidates identified. What was so odd about it? It wasn't exactly a direct message, mind you. Instead, it was a subtle but persistent fluctuation in radio waves detected by a sensitive array of telescopes. Imagine picking up a faint, rhythmic pulse where there should only be silence or random cosmic noise. This wasn't the kind of broad, chaotic energy you'd expect from a natural celestial body tumbling through space. It had a degree of regularity, a pattern that defied easy astronomical explanation. When the team analyzing the data stumbled upon this anomaly, the initial reaction wasn't excitement about aliens. It was confusion, followed by rigorous checking and rechecking of their equipment and data processing. Could it be interference from satellites, ground-based radio chatter? Natural astrophysical phenomena they hadn't accounted for. They exhausted every conventional explanation they could think of, and still, the signal remained tied to the trajectory of this specific interstellar visitor. The sheer unexpectedness of this detection was what made it so significant. Until then, interstellar asteroids were simply seen as inert rocks or ice balls. The idea that one might be actively emitting something, even a seemingly simple radio fluctuation, was completely off the standard script. It wasn't a strong signal, not a booming transmission, but its presence, its persistence, and its association with an object from another star system were enough to raise eyebrows and, more importantly, to ignite a focused effort to look for other anomalies. This single, puzzling detection was the spark that lit the fire, prompting scientists to begin scrutinizing data from other interstellar objects with a new, more open-minded perspective, specifically looking for anything that deviated from the expected cosmic silence. Following that initial puzzling detection, another signal emerged from a different interstellar candidate, and this one had a characteristic that immediately grabbed attention: repetition. Unlike the first signal, which was more of a consistent, low-level emission, this new anomaly displayed a distinct pattern, almost like a cosmic heartbeat or a subtle cosmic pulse repeating at regular intervals. It wasn't a perfectly precise beat, there was some minor variation, but the underlying periodicity was undeniable. Imagine monitoring a quiet radio frequency and suddenly picking up a sequence of beeps, pause, consistently appearing at roughly the same interval. That kind of predictable pattern in space is highly unusual for natural celestial objects. Why is a repeating pattern so significant when we're talking about potential artificial origins? Well, nature tends to be messy and chaotic on many scales. While pulsars emit incredibly regular pulses, they are neutron stars, far more massive and energetic than any asteroid, and their signals have distinct characteristics we understand. The kind of repetition observed from this small, rocky visitor didn't fit any known natural astrophysical phenomenon associated with asteroids or comets. Natural sources of radio waves from these objects are typically broadband and irregular, generated by things like microfracturing or interaction with the solar wind. A structured, repeating signal suggests something deliberate, something designed to be periodic. It raises the question, what could possibly cause a small, cold rock drifting through space to emit a signal that goes on and off at regular intervals? Immediately, scientists began working through the standard checklist of potential explanations. Could it be something on Earth interfering with the telescopes? They calibrated instruments, cross-referenced with observations from other facilities, and checked against known sources of radio interference. None of these explanations panned out. Could it be some bizarre, never-before-seen natural process happening on or around the asteroid? They considered everything from unusual internal activity to interactions with interstellar dust, but nothing could convincingly explain the observed periodicity and the specific pattern of the signal. The fact that conventional explanations were failing made this repeating signal particularly compelling and, for some, tantalizingly suggestive. It pushed the boundaries of known astrophysics and kept the mystery alive. Beyond the puzzling repetition, things took another strange turn with a pair of signals that showed something entirely different: intense energy spikes. These weren't the subtle fluctuations or rhythmic pulses we discussed. These were sudden, powerful bursts of energy, like cosmic lightning strikes, associated with two separate interstellar objects. Let's call them signals 3 and 4 for simplicity's sake. The sheer power packed into these fleeting moments was what astronomers found so baffling. The energy levels detected during these spikes were orders of magnitude higher than anything you'd expect from an inert rock or even a mildly active comet. Imagine the typical, faint energy signature of an asteroid as a dim nightlight. These energy spikes were like someone suddenly flipping on a stadium floodlight for a fraction of a second. Natural processes that can generate energy in space, like tiny impacts or electrostatic discharges, simply couldn't account for the detected magnitude. It was like trying to explain a volcano erupting by saying a pebble fell down a hill. Scientists immediately looked at possibilities like collisions with smaller debris, but the characteristics of the spikes didn't match impact signatures. They also considered phenomena like plasma interactions with the interstellar medium, but again, the energy levels and the suddenness of the bursts didn't align with known behaviors. These spikes were a significant departure from the expected peaceful glide of an asteroid through space, presenting yet another layer of mystery that defied conventional astrophysical explanations. Adding to the list of anomalies, another signal, let's call it signal number 5, stood out not for its pattern or intensity, but for its wavelength. Now, in astronomy, the wavelength of light or radio waves we receive from space acts like a fingerprint, telling us a lot about what produced it. Different elements, molecules, and physical processes emit or absorb energy at very specific wavelengths. Think of it like a cosmic barcode. For example, hydrogen atoms emit light at a precise wavelength of 21 centimeters, which is a key signature for mapping gas in the universe. Water molecules have their own unique set of wavelengths, and so do various minerals and materials you'd expect to find on an asteroid. But when scientists analyzed signal 5, its wavelength didn't cleanly match any of the usual suspects associated with a cold, rocky body in space. It wasn't the signature of common elements you'd expect, nor did it fit the profiles of known astrophysical noise or human-made interference they could identify. This signal was detected by a global network of radio telescopes, each one contributing data to try and pinpoint its source and characteristics. Analyzing this kind of data is incredibly challenging. It requires filtering through tons of noise and accounting for countless variables, from atmospheric conditions to the subtle movements of the object itself. The fact that this signal persisted across multiple observations and that its specific wavelength remained unidentifiable against the standard cosmic backdrop made it profoundly perplexing. It was a wavelength that simply didn't belong, a note played out of tune in the expected symphony of asteroid emissions. Now, let's shift gears slightly and talk about a signal that was less like a sharp spike or a rhythmic beat and more like a steady drone. This was signal number 6, and some scientists informally described it as a hum. Imagine tuning into a radio frequency, and instead of hearing static or bursts of noise, you detect a low-frequency, persistent tone, almost like a soft buzz that just wouldn't go away. This hum was detected within a specific range of radio frequencies, lower than many signals we typically monitor for astronomical observations, but definitely distinct from background noise. And critically, it wasn't a fleeting event. It lingered, detectable for several observation periods as the interstellar object traveled across the sky. Why is a continuous hum from an asteroid so strange? Well, asteroids are generally considered cold, inert bodies. They reflect sunlight and might occasionally release some gas if they contain volatile materials like ice, but they aren't expected to generate their own sustained, low-frequency radio emissions. It's like expecting a simple rock on Earth to suddenly start emitting a steady sound. The sheer act of continuously emitting energy at a detectable level for an extended period is highly unusual for a natural, non-active celestial object. Initially, researchers explored all the usual suspects to explain this persistent hum. Could it be thermal radiation, the faint heat signature of the asteroid itself? While objects do emit thermal radiation, it's usually broadband and not concentrated at specific, detectable radio frequencies in this way. Could it be some interaction with the solar wind or the weak magnetic fields in interstellar space? Again, known interactions typically don't produce such a sustained, focused emission in this specific frequency range. Were the telescopes picking up some distant natural phenomenon aligned with the asteroid's path? They meticulously checked star charts and catalogs of known radio sources, but nothing matched the characteristics of the signal tied to the object's movement. Each conventional explanation they investigated seemed to fall short, leaving the persistent hum of signal 6 as yet another puzzling piece of the cosmic puzzle. Moving on to another fascinating puzzle, signals 7 and 8 present a different kind of anomaly, one related to how these interstellar objects are reflecting light. Astronomers use something called a light curve to learn about a celestial body. Imagine watching an asteroid as it tumbles through space. As its shape changes relative to our viewpoint, the amount of sunlight it reflects back to us changes. If it's a long, skinny object turning end over end, you'd see the light dim when you're looking at its narrow side and brighten when you see its wider side. Plotting this varying brightness over time creates a light curve. This curve is like a signature. It tells us about the object's shape, how fast it's spinning, and even if it has any large features on its surface. A regularly shaped asteroid tumbling smoothly will produce a predictable, repeating pattern in its light curve. However, with signals 7 and 8, the light curves were anything but predictable. Instead of the smooth, symmetrical variations you'd expect from a simple tumbling rock, these objects showed sudden, sharp dips in brightness or highly asymmetrical patterns that changed unexpectedly. It wasn't just a matter of an irregular shape. Scientists modeled countless possible shapes and rotation rates, and none could fully explain the observed light variations. Think of it like watching something spin that suddenly, for no apparent reason, momentarily flashes much dimmer or brighter than it should at irregular intervals. These sudden, unexplained dips or the persistent lopsidedness of the light variations hinted at something more than just a simple rotation. it raised questions about whether parts of the surface were briefly being obscured in unusual ways, or if something was temporarily blocking the light, or perhaps if the reflectivity of the surface itself was changing. These light curve oddities were another piece of the puzzle that didn't fit the standard picture of a passive interstellar asteroid simply passing by. Adding another layer to this cosmic puzzle, signals 9 and 10 brought a whole new dimension to the mystery, suggesting the presence of something far more complex than just rock and ice. These two signals, detected from different interstellar objects, hinted at possible molecular signatures, suggesting the presence of organic molecules or other unexpected compounds. Think of it like this: when scientists analyze the light or radio waves coming from a celestial object, they're essentially looking at its chemical fingerprint. Different atoms and molecules absorb or emit light at specific wavelengths, leaving telltale lines or patterns in the spectrum. It's a bit like identifying materials by scanning their unique barcode. Normally, when we look at asteroids and comets, we expect to see signatures of basic elements and simple molecules, things like water ice, carbon monoxide, or silicate minerals, the common building blocks of planetary systems. However, the spectral analysis of the light reflecting off or energy being emitted by the objects producing signals 9 and 10 revealed patterns that didn't fit this standard picture. There were indications of more complex molecules, perhaps hydrocarbons or other organic compounds, the kinds of molecules that are the carbon-based foundation for life as we know it here on Earth. Now, finding organic molecules isn't entirely unheard of in space. They exist in molecular clouds and on some meteorites that fall to Earth. But detecting them on an interstellar asteroid, an object that has potentially traveled light years through the harsh vacuum of space, is particularly intriguing. These molecules would have been exposed to intense radiation, extreme temperatures, and the vacuum of interstellar space for potentially millions or even billions of years. For them to survive that journey and still be detectable suggests either a remarkable resilience, a protective mechanism, or perhaps even continuous production. The potential implications of finding such molecules are profound. It could mean that the building blocks of life are being transported across the galaxy, seeding new planetary systems. Or, in a more speculative vein, it could hint at processes occurring on or within these objects that are far more complex than simple geology or ice sublimation. It adds a fascinating biological whisper to the purely physical mysteries we've been exploring so far. Adding to the strangeness, signal number 11 presented itself not as a hum, a pulse, or a spike, but as something observers described as a chirp. Imagine a brief, high-pitched burst of energy that appeared out of nowhere and vanished just as quickly, lasting only a fraction of a second. This transient, fleeting nature is what made the chirp signal particularly vexing for researchers. Detecting anything this short-lived in the vastness of space is a challenge in itself, like trying to catch a firefly in a hurricane. And because it didn't repeat, there were no follow-up chances to confirm its presence, analyze it further, or pinpoint its characteristics with greater precision. These kinds of short-duration, non-repeating signals are incredibly difficult to study. Unlike a consistent or rhythmic signal that you can observe over time, allowing for multiple measurements and cross-referencing between different instruments, a single, quick event leaves very little data to work with. It's like hearing a single word whispered in a noisy room. You catch a glimpse, but it's hard to be certain what was said or who said it. Yet, despite the difficulty, even a single, unexplained anomaly can be highly significant. In the search for the unusual, a one-off event, if it can't be explained by known natural processes or instrumental glitches, still raises important questions and can indicate that something happened, even if we don't know exactly what. Confirming whether this chirp was real, a genuine signal from the interstellar object, or just some form of interference was a major effort. The data had to be meticulously scrutinized. Did other telescopes happen to be looking in the same direction at that exact microsecond? Were there any known sources of terrestrial or satellite interference that could mimic such a signal? Could it be an unusual interaction with cosmic rays hitting the detector? Each possibility was investigated, and in this case, none provided a definitive explanation that could fully account for the detected chirp and its characteristics. The challenge lies in the lack of confirming data points. Attributing a transient signal like this to a specific cause, especially when it originates from a distant and unvisitable object, pushes the limits of our current observational capabilities and leaves the chirp as yet another unclassified cosmic event. Let's turn our attention now to signals 12 and 13, which introduce another strange characteristic: polarization peculiarities. So, what exactly is polarization when we talk about light or radio waves? Imagine light or radio waves as tiny ripples or vibrations. Normally, these vibrations happen in all directions, perpendicular to the wave's movement. Polarization is when these vibrations are aligned or oriented in a specific direction. Think of passing those waves through a slotted filter like polarized sunglasses. Only the waves vibrating in a certain direction can get through. Natural sources of light and radio waves in space tend to have predictable polarization patterns. Light scattered off dust, for example, has a specific type of polarization, and radio waves from different cosmic phenomena like pulsars or nebulae also have characteristic polarization signatures that scientists understand and can anticipate. But with signals 12 and 13, the polarization detections were just off. They didn't match the expected patterns for light scattered from a rocky surface, or the polarization signatures of any known natural astrophysical phenomena we might expect from a cold asteroid drifting through the void. The way the vibrations of the radio waves were oriented seemed unnatural, almost as if they were deliberately aligned in a way that doesn't occur through standard cosmic processes. This wrong or unexpected polarization is another piece of evidence that pushes these signals away from being easily explained by conventional astronomy. It strongly suggests that whatever is producing these signals is doing so through a mechanism that is not typical for an asteroid, hinting at an emission process that is decidedly non-standard. Next on our list of head-scratchers is signal number 14, which was described as a broadband blast. Now, when we talk about radio signals from space, they usually occupy a specific, narrow range of frequencies, like tuning into a single radio station. Think of the hydrogen signal at 21 centimeters we mentioned earlier. That's a very precise frequency. Different cosmic processes naturally emit energy at particular frequencies based on the physics involved. But signal 14 was different. It was detected simultaneously across a very wide spectrum of radio frequencies, like every single radio station suddenly started broadcasting at once. For an asteroid, a cold, rocky body, to emit energy across such a broad range is highly unusual. Natural broadband emissions from asteroids are generally extremely weak and related to things like their thermal heat signature, which is usually far below detectable levels for this kind of observation. There are natural cosmic phenomena that produce broadband emissions, like the static of distant cosmic microwave background radiation or the powerful bursts from solar flares, but those are easily identifiable and don't originate from a tiny object like an asteroid. A broadband signal from an asteroid is like hearing a full orchestra coming from a single violin. It just doesn't fit the expected physics. Scientists considered possibilities like a sudden impact event, which could generate a brief broadband radio pulse. However, the duration and characteristics of signal 14 didn't perfectly align with known impact signatures. They also looked into potential interactions with charged particles in space, but again, those interactions usually result in emissions within more defined frequency ranges. The puzzle with this broadband blast was that it didn't fit neatly into any established category of natural radio emission we'd expect from an interstellar asteroid. suggesting a process that is either entirely unknown or perhaps not natural at all. Let's move on to signals number 15 and 16, which presented yet another layer of confusion related to the strength of the signals. When we receive radio waves from a distant object, their power, or how strong they are, typically decreases predictably with distance. It's like a flashlight beam. The farther away you are, the dimmer it appears. Also, if the object is rotating, the signal might get stronger or weaker depending on which part of it is facing our telescopes, especially if the emission isn't uniform across its surface. These are expected, natural variations that scientists can easily calculate and account for. However, signals 15 and 16 showed fluctuations in power that simply didn't follow these rules. The variations observed were erratic and didn't correlate with the object's calculated distances or their apparent rotation rates determined from their light curves. Imagine monitoring a signal that should be steadily fading as the object moves away, but instead it suddenly gets stronger for a bit, then weaker in an unpredictable fashion, independent of its position or how it's oriented towards us. This wasn't a smooth, gradual change. It was more like someone intermittently turning the volume up and down randomly. This disconnect between the expected power changes and the observed fluctuations was baffling. Could these power fluctuations be caused by some internal process within the asteroid itself? This possibility led researchers down some less conventional paths. We know that asteroids can have internal structure, perhaps even voids or pockets of different materials. Could some kind of geological activity, however minor, be intermittently focusing or blocking the emission? Or perhaps a release of trapped gas? While these are usually associated with comets, some asteroids might retain subsurface ice. Could an unusual physical process like triboelectric charging from internal shifts or even acoustic vibrations be somehow modulating an underlying emission? These are highly speculative ideas when applied to a cold, inert rock, but the unexplained power fluctuations were so far outside the norm that they forced scientists to consider possibilities that go beyond standard asteroid physics. It highlights how truly anomalous these specific signals appear when measured against our current understanding. Adding another layer to the enigma, signal number 17 brought a new clue to the table, hints of directionality. Now, when natural cosmic sources emit radio waves, they typically broadcast in all directions, like a light bulb illuminating a room. The energy spreads out spherically, becoming weaker and weaker the farther away you are. But signal 17 seemed different. Analyzing the data suggested that the signal was stronger when the interstellar object was oriented in a particular way relative to our telescopes, almost as if the emission was focused into a beam, like a flashlight pointed directly at us. This wasn't a perfectly clear, undeniable beam, mind you. The evidence was subtle, found through sophisticated analysis of signal strength variations as the object rotated and its position in the sky changed. Why is a directed signal such a big deal when we're talking about potential artificial origins? Well, focusing energy into a beam is precisely what we do here on Earth when we want to send a message or transmit power efficiently over long distances. Think of communication antennas or radar systems. They are designed to direct signals towards a specific target rather than broadcasting indiscriminately. Natural cosmic phenomena generally don't produce highly directional emissions from small objects like asteroids. Therefore, any indication of beaming immediately raises the question of intent. Could something be deliberately focusing this signal? The observations that suggested this directionality for signal 17 were challenging to interpret definitively. It required incredibly precise measurements of signal strength at different times and correlating those with the object's calculated orientation. Was the variation due to the shape of the object itself, perhaps acting like a natural, albeit accidental, reflector? Could it be caused by some complex interaction with its environment that we don't understand? Disentangling these possibilities from a genuine, artificial beam is incredibly tough with the limited data we have. Proving directionality beyond a shadow of a doubt would require multiple observations from different vantage points, ideally with telescopes spread across the globe, all detecting the signal strongest when the object is aimed their way. Without that kind of corroborating evidence, the hint of directionality for Signal 17 remains just that a tantalizing clue, adding to the list of properties that make these interstellar visitors so much more intriguing than simple space rocks. Signals number 18 and 19 threw another curveball into the mix, and this time it was all about timing. These signals didn't just appear, they seemed to turn on or off at specific moments in the interstellar object's journey or its rotation cycle. Now, usually when we see variations in a signal from a celestial body, it's predictable. For instance, if an asteroid has a highly reflective patch on one side, the signal might strengthen each time that patch rotates into view. Or if a signal is related to the sun's energy, it might be stronger when the object is closer to the sun. These are straightforward, geometrically driven changes. But with signals 18 and 19, the timing just didn't line up with any of these simple external factors. The signals would activate or cease in ways that didn't correlate with the object's position relative to the sun, the Earth, or even its own determined rotation period. Imagine an object spinning predictably, but a signal coming from it switches on and off seemingly at random points in its spin, or perhaps only when it crosses some invisible line in space that has no obvious astrophysical significance. This unexpected timing ruled out many of the straightforward explanations, like simple reflection of sunlight or interaction with the solar wind, because those are dependent on the object's position and orientation. So, if it wasn't about where the asteroid was or how it was spinning in relation to us or the sun, what could be controlling the timing of these emissions? This is where speculation really takes off. Could it be something happening inside the object, perhaps internal processes like shifts in material, some form of internal energy release, or even the activation of something deliberately timed? Or could it be related to some interaction with the incredibly tenuous interstellar medium, perhaps triggering emissions when the object passes through a region of slightly denser gas or dust, even if that density change is too small for us to detect directly? The fact that the timing is so disconnected from the basic orbital and rotational mechanics we understand is what makes these signals such enduring enigmas, suggesting that whatever is producing them operates on its own independent schedule. Signal number 20 added yet another layer of complexity, suggesting the possibility of a harmonic. Now, to understand what a harmonic means in this context, think about musical instruments. When you pluck a guitar string, it vibrates at a main frequency, which is the note you hear, say a C. But the string also vibrates at multiples of that main frequency, 2 times the frequency, 3 times, 4 times, and so on. These multiples are called harmonics, and they're what give each instrument its unique tone or timbre. In radio waves, a harmonic signal would be detected at a frequency that is a precise multiple of a lower, fundamental frequency. So, why is finding a possible harmonic from an interstellar asteroid so intriguing? Because natural cosmic processes usually don't generate signals with such precise, integer multiple frequency relationships. It's the kind of structured emission you'd more likely associate with something deliberately engineered. The detection of signal 20 at, say, frequency X led some researchers to speculate that it might be the second or third harmonic of a much weaker, or perhaps directed, signal at a lower frequency, like X divided by 2 or X divided by 3, a fundamental frequency that we hadn't managed to detect directly. The challenge, of course, is confirming that signal 20 truly is a harmonic without actually detecting that fundamental frequency. It's a bit like hearing a faint echo but never hearing the original sound. Scientists performed meticulous analysis to see if the observed frequency of signal 20 was a precise multiple of any plausible, naturally generated frequency range, but those attempts came up short. They also considered instrumental artifacts or atmospheric effects that could create spurious harmonics, but these possibilities were difficult to confirm or rule out definitively. The speculation that signal 20 might be a harmonic, while not a definitive conclusion, added a fascinating dimension to the mystery, hinting at a potential underlying structure or complexity to the emissions that we haven't yet fully grasped. Diving into the remaining signals, 21 and 22 presented a particularly intriguing puzzle, transient bursts that fired off at what seemed like very specific moments. These weren't continuous hums or rhythmic pulses, but rather sudden, powerful injections of energy, almost like a quick flash, that researchers noticed were consistently occurring when the interstellar object was in a particular orientation during its spin, or at a specific location along its orbital path. Imagine a lighthouse beam that only flashes briefly when the light source is pointing directly at you, but in this case the flashes were energetic bursts, and they happened with a curious regularity related to the object's movement. This wasn't the kind of random flaring you might expect from a simple tumbling rock. The question immediately became, what could be happening at these specific points in space or time to trigger such bursts? It strongly suggested localized activity. Perhaps there were specific regions on the asteroid's surface or within its structure that were the source of these emissions. Could these points correspond to some visible features, like unusually reflective patches, darker areas, or even small craters? Unfortunately, our ability to resolve detailed features on these distant, small objects is limited, so direct visual confirmation of any surface correlation wasn't possible with current technology. However, the timing of the burst strongly hinted that whatever was causing them was tied to a specific part of the asteroid itself. Could it be something like localized outgassing from trapped volatiles being exposed to sunlight at a certain angle due to the object's rotation? Or perhaps some kind of electrostatic discharge built up and suddenly released from a particular region with unusual electrical properties? Other possibilities included the fracturing of specific materials under stress, releasing energy, or even internal processes reaching a critical point at regular intervals due to tidal forces from distant stars or planets, though that's highly speculative. The fact that these powerful, transient bursts were so precisely tied to the object's state of motion was a significant clue, pointing towards a source that was not randomly distributed but rather concentrated in specific locations, adding another layer to the mystery of what lies beneath the surface of these enigmatic interstellar travelers. Venturing further into these cosmic oddities, signal number 23 presented yet another variation on the theme of unexplained energy. This one wasn't about dramatic spikes, sudden flashes, or rhythmic pulses. Instead, it was characterized as a remarkably low-level, almost whispering emission, but one that persisted over long periods whenever the interstellar object was within the detection range of our telescopes. Think of it not as a shout or even a clear word, but more like a faint, continuous murmur coming from the depths of space. Now, picking up signals this week is incredibly difficult. It's like trying to hear a pin drop in a noisy factory. Our telescopes and instruments are highly sensitive, but there's always background noise, radio waves from Earth's technology, cosmic microwave background radiation, and emissions from countless other celestial objects. Confirming that a faint signal is genuinely coming from a specific, distant object and isn't just static or accidental interference is a painstaking process. It involves meticulously comparing data from multiple observations, cross-referencing with different telescopes if possible, and employing sophisticated data processing techniques to filter out everything that's not tied to the object's movement across the sky. The sheer difficulty of isolating and confirming such a weak signal means that any team reporting one has likely gone through an exhaustive verification process. Despite its faintness, the persistence of signal 23 is what makes it noteworthy. A continuous, even weak, emission from an object that's supposed to be a cold, inert rock is still highly unusual. Natural emissions from asteroids are typically transient events like impacts or perhaps very low-level thermal radiation. Sustained energy output, no matter how slight, requires a continuous power source and emission mechanism. This isn't the kind of behavior we expect from a simple chunk of rock and ice tumbling through space, which is why even this barely their hum adds another layer to the profound mystery surrounding these interstellar visitors. And finally, we come to signals number 24 and 25, the ones that have truly left scientists scratching their heads the most. These two signals stand out because they seem to combine several of the strange characteristics we've already discussed, or they exhibited entirely new, completely baffling properties that defied all the conventional astrophysical explanations. Take signal 24, for example. It wasn't just a repeating pulse or a sudden spike. It seemed to incorporate elements of both. It would emit in a rhythmic pattern, but within that pattern were bursts of intense energy, a structured emission containing unexpected power surges. Imagine a clock ticking predictably, but every few ticks it lets out a sudden, loud noise. Furthermore, the frequency of these pulses seemed to slightly shift over time in a way that didn't easily correlate with the object's movement or its environment. This combination of periodicity, intense bursts, and frequency drift made it incredibly difficult to model using known natural processes. Then there's signal 25, which presented a completely different kind of puzzle. This signal wasn't primarily detected as radio waves, but rather as an unusual energy signature in the infrared spectrum, the kind of heat radiation that objects emit. What was strange about it was not just its presence. Objects in space do emit infrared light based on their temperature, but the specific pattern of the emission. It was incredibly narrow band, meaning the energy was concentrated in a very precise, confined range of infrared wavelengths, rather than spread out like a typical thermal signature. It was like detecting heat, but only at a single, specific color of heat, which is not how everyday objects radiate. Compounding the mystery, this narrow-band infrared emission also seemed to fluctuate in intensity in a non-random way, almost as if it were being modulated or controlled. Neither of these signals, 24 with its complex radio behavior or 25 with its narrow band, modulated infrared, have found a satisfactory explanation within our current understanding of asteroid physics, leaving them as the most potent symbols of the unexplained mysteries these interstellar visitors carry. With these 25 strange signals on the table, the scientific community has been working overtime trying to find explanations within the realm of known physics and astrophysics. After all, the extraordinary claims require extraordinary evidence, and the first step is always to rule out every possible natural phenomenon. So, what are some of the leading hypotheses that attempt to explain these bewildering emissions without resorting to something truly exotic? One idea revolves around less understood geological processes that might be occurring on these interstellar rocks. We know asteroids can experience internal stresses from cooling, solidification, or even tidal forces from nearby stars or planets during their long journeys. Could these stresses cause microfractures that release bursts of energy, perhaps even electromagnetic energy? Some scientists have theorized that piezoelectric effects, where certain crystals within the rock generate an electric charge when subjected to mechanical stress, could be responsible for some of the observed signals, particularly the transient spikes. While plausible in theory, the challenge here is that the energy levels detected in some of the spikes seem far higher than what simple geological fracturing or piezoelectric effects would typically produce on an object of this size. It's like expecting rubbing your feet on the carpet to generate enough electricity to power a city. The scale doesn't quite match up with what we understand about these processes in rocks. Another compelling natural explanation that gets tossed around is outgassing from buried ice or other volatile materials. While many asteroids are thought to be primarily rocky, some, especially those potentially originating from the colder outer regions of another star system, might contain significant amounts of water ice, carbon monoxide ice, or other frozen gases beneath their surface. As the asteroid warms up, perhaps as it gets closer to our Sun or another star, these buried volatiles could turn into gas, creating pockets of pressure that eventually rupture through the surface in sudden bursts. This kind of outgassing is a well-known phenomenon for comets, producing their distinctive tails. However, these interstellar objects don't generally display the typical cometary coma or tail that accompanies extensive outgassing. Could the ice be buried deep enough that the gas is released in a more focused, perhaps even semi-explosive way without creating a visible atmosphere? This might potentially explain some of the sudden energy spikes or even produce localized jets that could affect the asteroid's rotation and thus its light curve in strange ways. The difficulty is that the observed signals, particularly the repeating patterns or the narrowband emissions, don't perfectly match the characteristics expected from typical outgassing events. Those tend to be more chaotic and broadband. Then there's the fascinating possibility of unusual compositional reactions. What if these interstellar visitors are made of materials we haven't encountered before in our own solar system's asteroids? Different star systems can have different abundances of elements and different conditions during planet formation. Could there be exotic minerals or compounds within these asteroids that react with each other or with the interstellar environment in ways that generate radio waves or infrared radiation? Perhaps there are materials that become highly charged as they interact with the faint plasma in interstellar space, leading to electrical discharges. Or maybe there are compounds that undergo slow chemical reactions that release energy intermittently. For example, some materials can luminesce, emitting light or other forms of radiation after being exposed to cosmic rays. Pinpointing the exact reactions that could produce the specific characteristics of the 25 observed signals is incredibly challenging without knowing the precise composition of these objects. It's like trying to guess the ingredients of a complex dish just by smelling it from across the street. While the idea of novel compositions is certainly plausible, it remains a broad hypothesis that requires specific mechanisms to link a particular exotic material to the observed signals, and such explicit links are currently speculative. Finally, scientists have considered interactions with the stellar winds of our Sun, or even the extremely tenuous interstellar wind, the flow of charged particles and magnetic fields throughout the galaxy. As an interstellar asteroid rushes through this environment, it could interact with these fields and particles in complex ways. Could these interactions generate plasma waves or induce currents within the asteroid that lead to radio emissions? Perhaps the buildup and release of charge on the asteroid's surface as it moves through different magnetic field regions could contribute to the signals. This hypothesis might help explain some of the timing-related anomalies, as the interaction could depend on the object's position in its trajectory or its orientation relative to external magnetic fields. However, modeling these interactions precisely for an irregularly shaped, tumbling object traversing through a constantly changing galactic environment is incredibly complex. And again, matching the specific patterns, like the repeating pulses or the narrowband emissions, to known plasma physics or magnetic field interactions on this scale is difficult. Each of these natural hypotheses offers a piece of the puzzle, but none, individually or combined, seem to fully explain the complete range of the 25 perplexing signals, leaving the door wide open for other, perhaps more audacious possibilities. So, faced with these baffling signals that don't quite fit the mold of typical asteroid behavior, the next logical step for scientists is to ask, have we ever seen anything like this before? This is where the search for natural analogues comes in. Researchers are actively poring over data from countless known objects right here in our own solar system, everything from the most mundane asteroids in the asteroid belt to the icy comets streaking across the night sky, and even dwarf planets and moons. They are meticulously analyzing radio observations, infrared emissions, and light curves from these familiar celestial bodies, looking for any hint, any whisper, of the strange phenomena detected from the interstellar visitors. This search isn't just limited to our cosmic backyard. Astronomers are also studying data from observed phenomena in distant star systems, like young stellar objects with powerful outflows or exotic types of stars, to see if these signals could be explained by interactions happening on or between objects in those environments. The idea is simple. If these 25 signals are indeed caused by some natural process, even an unusual one, then there's a chance that process might occur elsewhere in the universe, perhaps on objects that are more accessible for us to study and understand. Finding a match, even a partial one, would provide a crucial clue, helping to demystify the interstellar signals by linking them to known astrophysical phenomena. It's like trying to identify a strange sound by comparing it to every sound you've ever heard before. However, despite these exhaustive efforts, the perplexing reality is that no clear, definitive natural analogues have been found for the specific combination of characteristics seen in these 25 signals. We see simple radio emissions from some asteroids, perhaps from minor outgassing or electrostatic charging, but not the structured pulses, the repeating patterns, the intense energy spikes, or the unusual wavelength. Comets exhibit outgassing, but their radio signatures are different, and they have visible comets and tails that these interstellar objects lack. While we observe complex phenomena around stars and galaxies, those occur on vastly different scales and involve processes far more energetic than anything we'd expect from a small, cold asteroid. The simple fact that we haven't found a convincing match among the billions of natural objects and phenomena we've observed makes these interstellar signals stand out even more sharply. It underscores their uniqueness and elevates the mystery, pushing us to consider explanations that lie outside the familiar textbook of astrophysics. Given the struggle to explain these 25 signals through natural processes, it's perhaps unsurprising that we arrive at what some might call the elephant in the room, the possibility that some of these emissions could have an artificial origin. When faced with phenomena that defy all known natural explanations, the question of whether something is deliberately causing these signals inevitably arises. For a small but vocal part of the scientific community and the general public, the sheer strangeness and unexplained characteristics of some of these signals, particularly the structured patterns, the precise timing, and the hints of directionality, point towards the idea that they might not be errant cosmic noise but rather something intentionally generated. While this is a truly extraordinary claim, and one that requires equally extraordinary evidence, dismissing it out of hand simply because it feels too much like science fiction wouldn't be responsible science. The concept that an interstellar object could be a vessel or probe from another civilization, whether active or dormant, has been explored in popular culture and science fiction for decades. The idea is that a highly advanced species might send probes to explore the galaxy, and these probes might possess the ability to communicate, navigate, or even interact with their surroundings in ways we would perceive as unusual. The fact that these objects are interstellar, originating from another star system altogether, naturally fuels this line of thought. If there is technological life elsewhere, sending probes to explore the cosmos seems like a logical step. And if those probes are visiting our stellar neighborhood, perhaps the signals we are detecting are signatures of their operation, perhaps communication signals, navigation beacons, or even residual energy from propulsion systems. It is crucial to emphasize that considering the artificial hypothesis is not the same as concluding it. Scientists approach this possibility with immense caution and skepticism, adhering to the fundamental principle that extraordinary claims demand extraordinary proof. Before seriously entertaining the idea of alien technology, every conceivable natural explanation, no matter how improbable it might seem at first glance, must be rigorously investigated and definitively ruled out. This is why the search for natural analogues and the detailed modeling of astrophysical processes are so vital. However, as that search continues to yield no clear answers for some of these signals, the artificial hypothesis quietly remains on the table, not as a preferred explanation, but as a possibility that, given the truly anomalous data, cannot be completely ignored in a responsible and open-minded scientific inquiry. But here's the thing, actually finding and analyzing these faint, strange signals from objects trillions of miles away is incredibly hard. Imagine trying to hear a whisper in the middle of a rock concert. That's essentially the challenge faced by the scientists listening to the cosmos. Distinguishing a subtle signal from the overwhelming background noise of space and our own planet is the first major hurdle. Every radio telescope on Earth picks up interference from satellites, cell phones, TV broadcasts, and even its own electronic components. Filtering all that out to find a genuine cosmic signal is a painstaking process requiring sophisticated algorithms and countless hours of manual data review. Then there's the issue of instrument calibration. Telescopes are incredibly sensitive instruments, but they're not perfect. Their responses can drift over time or be affected by environmental factors like temperature changes. Ensuring that what you think is a signal isn't just an anomaly caused by your equipment is crucial, and it requires constant, meticulous calibration and testing. It's like making sure your measuring tape is accurate before you start building something important. And even when one telescope picks up something interesting, confirming that detection is vital. Ideally, you want to see the same signal or one with similar characteristics observed by a different telescope, perhaps even one on the other side of the world, to rule out local interference and confirm it's truly coming from space. This kind of multi-observatory confirmation is incredibly difficult to coordinate, especially for fleeting or unexpected signals. The good news is that the challenges of detecting these weak, unusual signals are driving incredible innovation in astronomical technology and data science. Scientists are constantly developing new techniques to improve signal detection and analysis. This includes building more sensitive radio telescopes in radio-quiet locations, designing new digital signal processing algorithms that are better at identifying non-random patterns in noisy data, and using artificial intelligence and machine learning to sift through the vast amounts of information collected by modern observatories. New software is being written to automatically flag unusual patterns for human review, speeding up the process and potentially catching signals that might have been missed by older methods. There's also work being done on building arrays of smaller telescopes that can work together as one giant, incredibly sensitive instrument, further enhancing our ability to pick up faint whispers from the depths of space. These challenges, while significant, are fueling a new era of astronomical discovery, pushing the boundaries of what's possible in our quest to understand the cosmos and any potential signals within it. So, if these interstellar signals are so difficult to find and analyze, what comes next in this cosmic treasure hunt? The good news is, the scientific community isn't standing still. There's a real buzz of excitement and a growing push to develop the next generation of tools and strategies specifically designed to tackle the mystery of interstellar objects and any signals they might be carrying. One of the most promising avenues involves building telescopes with even greater sensitivity and resolution than the ones we have now. Imagine a telescope so powerful it could spot a tiny, unexpected flicker of light from a faraway galaxy. That's the kind of leap we're talking about. New radio telescope arrays are being planned or are under construction in remote, radio-quiet locations, places far away from human-generated interference, which will be able to listen in on fainter signals and across wider frequency ranges than ever before. Similarly, next-generation optical and infrared telescopes, both on Earth and in space, will provide sharper images and more detailed spectral analysis, helping us learn more about the physical composition and characteristics of these fleeting visitors, which could shed light on the origin of the signals. These more advanced instruments are like upgrading from a simple magnifying glass to a powerful microscope. They'll allow us to see and hear things we couldn't before, potentially revealing the true nature of these perplexing emissions. Beyond the powerful new eyes and ears on the sky, the future of interstellar signal hunting also relies heavily on dedicated observational campaigns. While lucky detections like Oumuamua have been serendipitous in the past, there's now a push for more proactive searches. This involves planning specific telescope time to monitor areas of the sky where interstellar objects are most likely to appear, based on our understanding of galactic dynamics. It also means developing rapid response protocols so that when a new interstellar candidate is detected, telescopes around the world can quickly pivot and gather as much data as possible before the object zips away, which often happens very quickly. Think of it like having a rapid alert system and a global network of photographers all ready to snap pictures the moment something interesting flies by. Additionally, proposed missions are even considering sending small, fast probes on trajectories that could potentially intercept future interstellar objects discovered closer to Earth, providing an unprecedented close-up look. While such missions are highly ambitious and face significant technological hurdles, the possibility of getting right up close to one of these visitors is incredibly exciting and would provide invaluable data to help solve the signal mystery. Crucially, unraveling the mystery of the 25 unexplained signals from interstellar asteroids isn't a task for just one team or one country. The vastness of space and the complexity of the data require global cooperation. International collaboration is absolutely essential in this field. Scientists from different institutions and different countries are already sharing data, comparing observations, and combining their expertise to analyze these perplexing signals. Future efforts will rely even more heavily on these partnerships. Imagine scientists in different corners of the world, each operating a powerful telescope, coordinating their observations to track a single distant object and share their findings in real time. This kind of collaborative network multiplies our observational power and allows for cross-verification, which is critical when dealing with such subtle and unusual signals. Sharing data openly and working together on analysis techniques will speed up the process of identifying natural explanations or perhaps ruling them out. This spirit of shared scientific endeavor, of combining resources and knowledge across borders, is perhaps one of the most powerful tools we have in our quest to understand these enigmatic travelers from beyond our sun. So there you have it, a deep dive into those 25 genuinely puzzling signals picked up from interstellar asteroids. We've explored the initial detections, the strange repetitions, the energetic bursts, the odd wavelengths, and the many other characteristics that just don't quite fit our standard model of how space rock should behave. While the scientific community absolutely prioritizes finding natural explanations, diligently checking for unknown geological processes, unusual compositions, or subtle interactions with their environment, the sheer number and the sheer variety of these anomalies truly keep the mystery front and center. It forces us to confront the possibility that these aren't just incredibly rare, almost miraculous natural phenomena happening in just the right way to mimic potential signs of something else. Could they, just perhaps, be hinting at something far more extraordinary originating from beyond the familiar boundaries of our own solar system? The quest for definitive answers marches on with every passing day, and every new interstellar visitor spotted provides another exciting opportunity to listen, to observe, and to learn. What do you think these strange signals could be? Are they the universe's way of showing us that natural processes are far stranger and more diverse than we currently understand? Or are they whispers from somewhere else entirely? Share your thoughts and theories in the comments below. I'd love to read them. And if you found this journey into the unexplained as fascinating as I did, make sure you hit that like button and subscribe to the channel so you won't miss out on future explorations of the cosmos' most intriguing mysteries.